Hello everyone. In this video, I will show you how to use Python to simulate a complete regulated power supply circuit. Recall that a regulated power supply circuit converts AC to DC and is robust to changes in input voltage and/or load resistance. The block diagram of a regulated power supply circuit is shown here. There are four main blocks. The transformer steps down the large amplitude AC voltage to produce an AC voltage with a smaller amplitude. The bridge rectifier converts AC to pulsating DC. The capacitor filter converts pulsating DC to smooth DC with a ripple. And the Zener regulator converts the smooth DC to constant DC. The input to the regulated power supply circuit is typically 240 volt RMS at 50 Hz or 120 volts RMS at 60 Hz. This map here shows the nominal voltage and frequency used by different countries in the world. In USA and Canada, 120 volt RMS at 60 Hz is used. In Australia, 240 volt RMS at 50 Hz is used. Many countries in Africa and Asia use voltage in the range 220 to 240 volt RMS at 50 Hz. In this video, we will assume that the input is 240 volt RMS at 50 Hz. In this video, we will use PySpice to simulate a regulated power supply circuit. PySpice is an open source Python module. We define the circuit in PySpice using a netlist. The circuit is then simulated using NGSPICE and results are plotted using NumPy and matplotlib packages. An introduction to PySpice is provided in another video in this channel. A link is provided at the end of this video. We can use the following resources as a starting point. PySpice comes with an excellent transformer example, which also defines the transformer model as a subscript. PySpice also has a bridge rectifier example, which you can find here. However, these examples do not consider the complete regulated power supply circuit. For instance, the rectifier example does not consider the transformer and the Zener regulator. This rectifier example uses a 1N4148, which is a signal diode. It does not use a proper rectifier diode such as 1N4002. Also, a Zener diode model commonly used in student projects such as 1N751 is not provided. In this video, I will show you how to solve these problems and successfully simulate a complete regulated power supply circuit. To get started with the circuit netlist, first we need to define the nodes in the circuit. This is shown here. Recall that a node is where two or more circuit elements meet. For instance, here, the transformer primary is connected between nodes Pri, short for primary, and ground. The transformer secondary is connected between nodes secondary plus and secondary minus, and so on. This node labeling will be used to translate the circuit into a netlist. Please pause the video now if you wish to study this in more detail. This is the transformer subcircuit from the example provided with PySpice. The primary and secondary windings are being modeled using winding resistance, capacitance, and inductance. Also, the coupling and the leakage inductance is being considered. The key parameters are listed here. Let's look at them in more detail. These are the values specified in the original example. In order to simulate an ideal transformer for a regulated power supply circuit, we set the coupling to 1 and the winding capacitance to 0. The winding resistance and the leakage inductance cannot be set to 0. So we give them very small values, 1 milliohm and 1 microhenry. We also increase the primary inductance to 100 henries. The turns ratio is input to this subcircuit. These settings allow us to simulate an ideal transformer for a regulated power supply circuit. This is showing you the PySpice commands to use to simulate the transformer. We import the transformer model and define the turns ratio. The input to the transformer is a sine voltage source. This is simulated here. It has this amplitude and 50 Hz frequency. This amplitude corresponds to 240 volt RMS. The sine source is connected between nodes Pri and ground. This sentence is defining the transformer. The primary winding is connected between nodes Pri and ground. The secondary winding is connected between nodes secondary plus and secondary minus. Note that in a regulated power supply circuit, one end of the secondary winding is not grounded. This is showing you the netlist for the diode bridge and the smoothing capacitor. For instance, diode D1 is connected between nodes secondary plus and smooth. The first node here is the node connected to the P side, and the second node here is the node connected to the N side. Similarly, diode D2 is connected between nodes ground and secondary plus, and so on. This is the netlist command for the capacitor. Here we have assumed a 1 millifarad capacitor connected between nodes smooth and ground. This part here is the label for the components. The diode model is defined in this file. Let's take a look at this in more detail. In order to understand the syntax of the diode model, we need to look at the NGSPICE user manual, which is available here. There are four main categories of the diode parameters: the PN junction DC parameters, the PN junction capacitance parameters, the temperature effects, and the noise modeling parameters. It is not necessary to define the values of all these parameters. The parameters commonly used are circled in red here. Please pause the video now if you wish to study these parameters in more detail. You can also find more details in the NGSPICE user manual shown here. We can use the LTSPICE diode models available online here to define the NGSPICE diode model. The 1N4002 LTSPICE diode model is shown here. The NGSPICE diode model subcircuit definition is shown here. Comparing these two models, except for parameter XTI, which has a slightly different name, all the other parameters have the same name, and they can be easily translated to the NGSPICE model definition. And this is the syntax we need to use. This subcircuit model needs to be stored in a 1N4002.lib file, and this file must be placed in the same folder as the main Python code. Please pause the video now if you wish to study this model in more detail. Next, let's move on to the Zener regulator. Recall that Zener regulator converts smooth DC to constant DC. The theory and explanation of a basic Zener regulator circuit is discussed in a different video in this playlist, and a link is provided at the end of this video. This is showing the PySpice netlist for the Zener regulator components. The Zener diode model is defined in this file. For proper orientation, the Zener diode is connected between nodes ground and output. These final two lines set up the transient simulation with a print step of 1 microsecond and a total simulation end time of 60 milliseconds. Since the time period is 20 milliseconds for a 50 Hz signal, this means that we are simulating 3 cycles of the input sine wave. Let's look at how to model the Zener diode. The 1N746 to 759 is a popular Zener diode family covering Zener voltages in the range 3.3 to 12 volts. The NGSPICE model of 1N751, which is a 5.1 Zener diode, is available here. This model is shown here. We can adapt it to define the NGSPICE model, which is shown here. Apart from the XTI parameter, which has a slightly different name, other parameters have the same name and we can copy the values across. In the NGSPICE model, the last few parameters here are temperature coefficients. Since we are running a transient simulation at a fixed temperature for a regulated power supply, these last few parameters are not included here. This sub-circuit model needs to be stored in a 1N715.lib file, and this must be placed in the same folder as the main Python code. Please pause the video now if you wish to study this model mapping in more detail. Finally, this is showing the standard declarations needed for PySpice to work and the plotting commands. We plot the primary and the secondary voltages together in one axis. We plot the secondary, the smooth DC, and the regulated DC output in one axis. Note that in order to plot the transformer secondary output, we must obtain it as a difference between two node voltages as shown here. Also in the plotting, we enable the cursor, which is related to these declarations. This is the complete Python code to simulate the regulated power supply circuit. We have the standard declarations at the top, the circuit netlist and the simulation commands, and finally the plotting commands. This code is also provided in the video description. The main code is in this file. The two model definitions are stored in these files. The modified transformer subcircuit is in this file. When we run this code, we obtain the results. This is shown here. We can move the cursor to read the values of interest. For instance, the secondary voltage peak is about 17 volts. This value can be read in the bottom right corner of the figure. The smooth DC output has a peak of about 15.6 volts, which is about 2 diode drops or 1.4 volts less than the peak of the secondary voltage. And the regulated output is about 5 volts as expected. Thank you for watching this video. The links to the videos mentioned in this video are provided here now. I had a lot of fun making this video and I hope that it is helpful to your learning, and you can now use Python to simulate your regulated power supply circuits.